If we connect a charged capacitor across an inductor, there takes energy exchange between the capacitor and the inductor. When the capacitor is fully charged, it has electrical energy. When this is connected to inductor coil, it starts discharging and hence loses electrical energy. But at the same time, the current in the inductor coil rises and hence it produces magnetic field in it. That is, energy stored in the inductor coil in the form of magnetic energy. When the capacitor is fully discharged, inductor coil has then maximum magnetic energy and hence it starts charging the capacitor in opposite direction. So energy oscillation takes place between capacitor and inductor coil. The electrical energy in the capacitor is converted into magnetic energy in the inductor coil and vice versa. This setup can be viewed in analogy with a spring attached with a mass. There, potential energy is converted into kinetic energy and kinetic energy is converted into potential energy. There, the oscillation is simple harmonic and now the energy exchange is also simple harmonic. I can analog this LC circuit with a spring model. Suppose initially there is no charge on the capacitor, then this is an equilibrium state. Now I charge this capacitor, I fully charge this capacitor, say up to capacitance C. Then the energy is stored in the form of electrical energy in the capacitor. Now we can relate it with a spring. Suppose I stretch the string. When I compress the string, say this is a positive distance, I compress the spring, the energy or the work done I do is stored in the form of potential energy. Okay, so this analogs with the potential energy with the electrical energy. Now if I switch this key on, the current will start flowing through this circuit and the current through the inductor will start increasing. That means the energy stored in this capacitor will be decreasing. Okay, so as soon as I release this, it will start oscillating, it will start moving. That means potential energy is converted into its kinetic energy when it moves. Okay, now when it has got enough kinetic energy, it will again stop. Then its kinetic energy is converted into potential energy. The same is the situation here. This gets discharged and the energy gets converted into magnetic energy, magnetic field energy. And now this inductor charges the capacitor but in opposite direction. Okay, now you will see when this is at extreme position, say minus X, again the potential energy is developed in this coil but in opposite direction. But now if you release, it will start oscillating. So this inductor coil charges the capacitor in opposite direction. Again this capacitor gets discharged. Then thus this electrical energy is converted into magnetic energy and magnetic is converted electrical energy alternately. Same as in the spring model where kinetic energy and potential energy are interchanging or alternately changing. The time period of the oscillation is 2 pi under root of m by k, where m is the mass, k is the spring constant. Okay, let's calculate the time period for LC circuit. Initially, if the capacitor is fully charged, there's whole energy stored in the electrical energy. Let minus q naught and plus q naught be the charges on the plates of capacitor C, and let I naught be the current. So initially when I touch this, current will start flowing in the circuit. Let that instance the current is I0. Okay, so after time t, at any interval of time, suppose the charge on the capacitor is here, it is plus q at time t and minus q at time t, then current flowing in the circuit will be I of t. Okay, the current will start flowing, it will start increasing in the inductor coil, and hence its magnetic field and magnetic flux linked with the coil starts increasing. So let plus q of t and minus q of t be charges on the plates of capacitor C, and I of t be the current at any instance of time t. Dynamic equations of motion. We can check the equations here by using Kirchhoff's voltage law. It's Kirchhoff's second law or voltage law. This states that the algebraic sum of all the voltage drops around any closed circuit is equal to resultant EMF in the circuit. Now the potential drop or potential difference of the capacitor is Vc, and potential difference of the inductor coil is Vl, which is equal to EMF. But here we have not applied any battery or any source of EMF, so this EMF is 0. So we have Vc plus Vl is 0. So Vc is minus Vl. So Vc is potential difference between the plates of the capacitor. It is Q by C. Okay, and VL is L di by dt, is the potential difference across the inductor coil. So by using this equation, Q by C is minus L di by dt. Okay, so this can be written as L di by dt minus Q by C. So di over dt will be equal to minus 1 by LC times Q. Okay, but you know that that the current is dq by dt. This can be written as q dot. Okay, now di by dt will be equal to d by differentiation of q dot, because I is q dot, so differentiation of I is q double dot. So we can write as q double dot is minus 1 by LC q. Let 1 by LC omega square be constant, this be a constant. Okay, then q double dot will be minus omega square q, and here you see the q double dot is directly proportional to minus q. Same as spring, in spring model we have acceleration negative times y. So this oscillation is simple harmonic. Okay, let's calculate the time period of this. So we have omega is 2 pi over t, which is 1 by under root of LC. All right, then time period will be 2 pi under root of LC. So this is the time period of